Hello everyone, thank you for watching this video. I'm going to introduce an interesting project, distributed processing for top K shortest paths using GraphX. This video was made by Avren, Deepika, Joshli, Ming, and Shrija. From the start, we wanted a project idea that was applicable to the real world and had some impact on people's daily lives. Graph algorithm was widely used in the real world, but most of the shortest path algorithms, like the Google Maps, are proprietary and are not available to the general public. So our approach is to finding top K shortest paths, which means multiple shortest paths in real-world route networks between two locations using the capability of the new technologies. But we face two big challenges: how to get multiple shortest paths, how to handle a large graph with many routes and intersections.
K shortest path, what and why? K shortest path are nothing but a list of the shortest path in increasing order of the cost. For example, in this graph, if A is the source and E is the destination, we see that there are multiple ways to reach from A to E. And K shortest path is nothing but the list of these shortest paths, but in increasing order of the cost. There are many scenarios where K shortest paths are required. For example, in road networks, if you have only one shortest path, this shortest path may be unavailable due to roadblocks or accidents. Also, this one shortest path may no longer be the best option due to higher traffic. Same goes with communication networks, where one node of the shortest path may stop working and we'll have to reroute the data via a different path. The general use case is the need to use the next best route. We've used a version of Yen's algorithm to get the K shortest path. How to handle large graphs or maps with thousands of nodes or cities. In our project, we use distributed and parallel processing of graph via multiple worker nodes using SPGraphX technology. Here, the input or the large graph is given as input to the master node. This huge graph is divided into smaller subgraphs and given to multiple worker nodes that run in parallel. Each of these worker nodes would compute and give a locally shortest path back to the master node. The master node will reassess all of these inputs it receives from each of these worker nodes and gives the user a list of the shortest paths.
Now let's look at the methods in which we implemented this research. To implement the K shortest path explained in the previous slide, we use a popular framework called Apache Spark, which quickly performs tasks on very large data. We also use GraphX, which is a distributed processing framework which is built on the Apache Spark. We built our implementation on Google Cloud Platform, which provides resources to run our implementation. To test our implementation, we use the following road network, in which the nodes represents the location and edges represents the connection between these two locations. Now let's look at the results and analysis of our implementation. We were successfully able to compute the K shortest path from our implementation, and then we made some analysis on the factors that affect the execution time. One of it is the impact of K, which is the number of shortest paths. We found that as the K increases, the execution time increases linearly.
Continuing with the result analysis, the next factor that we analyzed was the impact of n, that is the number of worker nodes assigned, and we could see that as n increased, the execution time decreased. We could also see the same when we saw the combined graph for impact of K analysis, that the execution time for worker nodes with worker nodes 2 was always greater than the execution time for worker node 6 for different values of K. Another factor is the impact of the graph size, which relies highly on the number of nodes and the connections between them. We used Pennsylvania, Texas, and California state road networks for this, and based on the experimentation results, we could see that as the dataset size increased, the shortest paths of decreasing weights were obtained in the same time, and also that when equal weight shortest paths were desired, the execution time increased as dataset size increased.
After carefully conducting all the experiment and observing the findings, we came to the conclusion that execution time is directly proportional to the number of K shortest path required. Execution time is inversely proportional to the number of worker machines. Execution time is directly proportional to the graph size. So all this conclusion can be derived in the equation given here, that execution time is proportional to the KD divided by N. But the limitation in our project is that we were able to expand with a limited number of worker machines. And in order for this conclusion, the assumption that one needs to be made were the weight of all the road connections needs to be equal to 1. But our feature improvement plan in our project that we can experiment KSPGraphX with more number of worker nodes, as we have seen here that execution time is inversely proportional to the number of worker machines. So as we increase the number of worker nodes in the cluster, the total execution time of the algorithm decreases. And second is that we can refactor and optimize the k-shortest path functions code to distribute additional tasks such as graph generation, identification of derivation nodes, etc. to worker nodes, which will reduce the burden on the master node and eventually make the algorithm more efficient. We would like to thank Dr. Quiros for all her support and encouragement in the project and course. We would like to thank the Computer Science Department for being supported throughout the semester, and also High Impact Practices HIP Student Symposium organizers for providing us opportunity to showcase all our efforts. And these are some references that have been used in this project. We would like to